Hi everybody, this is Chris Collison. We're continuing our course on quantum mechanics. So now we've got through a description and an introduction of the way of taking Cartesian coordinates and moving them into spherical coordinates. We're now going to look at chapter 6 of Donald Macquarie's book on quantum mechanics. Chapter 6 is called The Rigid Rotator and Rotational Spectroscopy. And we're going to be talking about here this kind of idea of a rotating dumbbell. And that rotating dumbbell, we might be thinking about that as maybe a hydrogen chloride molecule, something like this. But what we'll go on to think about is that this is a body of reduced mass rotating about a fixed center. So as I mentioned earlier, we're going to be thinking about spherical coordinates. So we're also going to find that the wave function, so the wave function is going to be a function of theta and phi in this particular case. We'll come into something called spherical harmonics. We'll also start thinking about the S and the P and the D orbitals. So this is going to transfer its way into the hydrogen atom. So we're well on our way now towards solving the Schrodinger equation for the hydrogen atom. Once again, we're going to find that the Schrodinger equation is lengthy. It's so that's a good way of describing it. It's going to be lengthy, and again, what we'll find in this particular section. So I'll be presenting the energies and the eigenfunctions without showing you explicitly how the solution comes about. So present those energies and the wave functions. So what we'll do first of all is actually jump straight into section 6.1 of the textbook, and that's called energy levels. So it goes directly into these energy levels and tells us right in that segment heading, it tells us what those energy levels are. So E is equal to h bar squared J times J plus 1 over 2I, and we're going to find J ends up being a quantum number. We're going to be thinking, as I mentioned earlier, about this as a rigid rotator. What does this mean? So really, when we think about this hydrogen chloride molecule in here, we're basically going to assume initially that the vibrational amplitude is small compared to the bond length, and so because it's small compared to the bond length, we can consider it to be a rigid rotator. So let's look at the next slide here and actually think about what that means. And of course, what we need to do in quantum mechanics is build ourselves up from a qualitative level. So what we imagine in here, so we have a rotation or an axis of rotation in here. This looks like it's all in one plane. It doesn't matter what the the important thing here is that rigid rotor is rotating about the black dot in the middle. So this is kind of our origin in here. And another thing here is that really, even though this looks like a rotation within the plane of the paper, we're actually got a rotation within. So we'll say the rotation within. Certainly an X, Y, and Z set of axes, right? So there's a three-dimensional look to this, and I'm going to stick with the diagram that I've got on the left-hand side here for the time being, because it demonstrates a couple of key points here. So we've got a mass M2, and we've got a mass M1 in here. So of course the mass M1 is moving around in a clockwise direction. Of course mass M2 is also moving around in a clockwise direction. The lengths here, so we've got these lengths. So we've got a length in here. That length represented also down here is length L2. We've got another length in here that's L1. So this is L1 and L2 respectively. When we add those together, we get a value L. What else can we say? So we've got this rotating. So this rigid rotor rotates at some frequency, and that frequency we're going to call nu rot, and it's in cycles per second or hertz. Since we know what the circumference of these circles is, we can basically write down, well, the circumference is going to be 2 pi L1, for example. There's the circumference for the mass M1. So therefore, the velocity, we'll call this the velocity of ball M1, is equal to 2 pi L1 nu rot. Okay, and so that's the velocity. That's what we care about. Later, of course, we're going to be thinking about the kinetic energy. We can also write the same thing about V2. Let's change color here just to be consistent. So V2 is equal to 2 pi L2 nu rot. So of course, there's a rigid rotor, so they're moving around the same number of cycles per second. The other thing we can recognize is that angular frequency is equal to 2 pi nu rot. So we can also write down these two expressions. So V2 is equal to L2 omega, or V1 is equal to L1 omega. What else can we say? So in the past with our harmonic oscillator, we basically transformed a two-body problem into an equivalent one-body problem. So we're going to try and do the same thing here. So remember, before we had two masses, M1 and M2, and we ended up talking about this reduced mass that was equal to M1 M2 over M1 plus M2. So that's going to still hold in this particular case. So what else can we do here? I'm going to write down a few key points. I'm also going to talk about the inertia. So generally speaking, the inertia is equal to mass times sort of the radius squared. Okay, so mass, it'll be an ml squared type situation. So what we're going to show in a second, by the way, is that the inertia is going to be equal to the reduced mass times L squared, and L, of course, down here is equal to L1 plus L2. So we're going to be thinking about this instead of having two masses sort of rotating around a point, as is shown in the diagram to the left. What we're going to imagine here is actually as if we've got one mass. Here's our mass, and the mass ends up having a reduced mass of mu, and it's going to be tethered to a center point, and that center point is a distance L away from that mu. And so where we want to get to is a way of thinking about the inertia as it being equal to mu times L squared. How do we get there? Well, I decided to go through this a little bit. So if we know what the reduced mass is in here, so here's our expression for reduced mass. This is mu, and L, of course, we now know is equal to L1 plus L2. So what I'm just going to show you in here is I've expanded this expression. So in the brackets over here, I've just taken L1 plus L2, and I've squared that in order to get this expression in the brackets. And then what I've done is I've expanded it further. So basically I've multiplied, I've expanded out the bracket to get this numerator in here. Another key thing that's important is that M1 L1 is equal to M2 L2. So that's important to recognize. That comes from the fact that indeed the center of mass right? So we've got this rigid rotor rotating around the center of mass, and I forgot to say that was what's going on here. So this is our center of mass in here, and so we can define the center of mass as basically m1 L1 is equal to m2 L2. So I've got some after expanding the bracket in here, what I now do is I'm going to collect some terms together, and what I'm ultimately going to do, so you can go through this yourselves, but basically I collect I need to get an m2 squared in here and an m1 squared in here, and then in the middle I've got this m1 m2 term. And I can do that by making this particular substitution in here to allow me to effectively write the numerator in this expression down here, in fact, as an m1 plus m2 squared term, and that allows me to cancel. Once I've done that, of course, then I can cancel it with the m1 plus m2 in the denominator, leaving me with L1 L2 multiplied by m1 plus m2. And then I go ahead and expand this a little bit more in here, and ultimately recognize that the inertia, so what we come out with in here is that the inertia is equal to the inertia of the first mass plus the inertia of the second mass, and therefore the final piece here is that we can say, if we come back to an earlier expression, of course we can have kinetic energy. Of course we're used to that being equal to half mv squared. So we also found out earlier that v1 is equal to L1 omega, v2 is equal to L2 omega. So when we plug this in, we're going to end up with our kinetic energy is equal to 1/2 L1 squared omega squared over m1 plus L2 squared omega squared 2 squared over m2. Putting this all together, we end up with kinetic energy is simply equal to I omega squared over 2. And from that, knowing from classical physics that angular momentum is equal to I omega, then what we end up with is the following expression for our kinetic energy. So what was the point of all that? The point of all that is to enable us to get some version of kinetic energy, some classical, sometimes this is called T, as being equal to L squared over 2 times the moment of inertia. Once we've come up with this solution in here, the classical description of the kinetic energy, we can start plugging in operators. So that's what we'll do in the next step. So let's actually take a quick summary. Let's take a look at these key equations that have been developed so far before we start going quantum. So what did we do already? We've considered some velocity v1 for the one of the objects on that rigid rotor. We've also thought about the velocity for v2, and since the angular frequency is equal to 2 pi nu rotation, then we can substitute omega into our equations for velocity, and we end up with v1 equals L1 omega and v2 equals L2 omega. We then, very simply, we start to think about the kinetic energy. In the textbook, the kinetic energy is referred to as capital T, and that's equal in all physics to half mv squared. And we can take now into account the velocities of both of these particles that are connected together. And so we end up now with an expression that includes the mass times the velocity for each of those particular balls, so m1 v1 squared over 2 plus m2 v2 squared over 2. The next thing we do is we kind of substitute and borrow for these. We substitute L1 omega in for V1, for example, and L2 omega for V2. This gets plugged into the expression that I'm pointing to here with the arrow. And so we've explained in the previous slide how we actually get a moment of inertia that's equal to m1 L1 squared plus m2 L2 squared. So again, what we can do is simplify to end up with a kinetic energy term now that takes into account the inertia of that system, the inertia of those two balls connected by that rigid rod. So the kinetic energy now ends up being inertia times omega squared over 2. And since from general physics, capital L, the angular momentum is equal to I times omega, then finally we end up with a kinetic energy in here in terms of capital L squared over 2I. So these are the kind of key equations. And of course, the next thing that we would be doing is we'd be saying, okay, what do we need to plug in order to get our quantum mechanical operator? And so we could write down T hat equals L hat squared over 2I. However, now that we've done that, we're also going to, so this is repeated at the top of this next slide. We're also going to recognize, if we remember back to page 148 in our table 4.1 of known quantum mechanical operators, we can, from that table, recognize that the quantum mechanical operator for kinetic energy is also given in terms of del squared, right? So del squared is di squared by di x squared plus di squared by di y squared plus di squared by di z squared. So again, there's our simplification, there's our del squared term in here. Another thing we can recognize is that really for this rigid rotor that's spinning around, at the moment there's no external forces, there's no potential energy therefore. So it's a fairly simple system. This we're going to find is helpful as we move towards more complicated systems. So we're going to say that the potential energy is equal to 0. However, as I've pointed out, we now need to work with spherical coordinates. This is going to make a lot more sense moving forward, and you're all probably looking at this, the equation at the bottom. We'll get to that. It turns out that we can do a conversion for del squared, right? So del squared being equal, of course, as I mentioned earlier, is equal to di squared by di x squared plus di squared by di y squared plus di squared by di z squared. So we can do a conversion, but that conversion is particularly tedious. It's worked out in a couple of the problems in chapter 6. We might go there later, but in this particular summary here, because we need to move on to thinking about our Schrodinger equation, we're going to present the result. And so you're thinking, wow, this is a really long equation. This is a really long operator. Do we really need to do spherical coordinates? Yes, we do. It turns out that the solution will end up being much more simple when we work with these spherical coordinates. So ultimately, what we're going to do is stop there and say, okay, we do have our kinetic energy operator. We do recognize still that there's this angular momentum operator term in here. We're later going to connect these two equations together. But first, after this slide, is we're going to do a little bit of work because in our particular case, we know that the R ends up being constant, and so it turns out that this first integral is going to essentially disappear because the R is constant. So let's look at that in the next slide. So in this next step, there's a certain amount of recap. Again, we remember that the potential is equal to 0. So let's remember that we're trying to build a Schrodinger equation, so we need the Hamiltonian operator. Since V is equal to 0, it's going to be equal to the kinetic energy operator, which here again, in concurrence with the textbook, we're going to use as capital T hat. And we've expressed how this ends up being, should be minus h bar squared del squared over 2m. So let's remember as well, we've got these two balls on a rigid rotor, and what we really want to do is work with the reduced mass. So we're going to substitute here for the mass. This is, remember, our general expression in here. So what we're going to do is substitute for the reduced mass, and this brings us to a new expression for the Hamiltonian operator, which includes our reduced mass. I've also shown in a previous slide how the moment of inertia is equal to the reduced mass multiplied by L squared. L, of course, is equal to L1 plus L2. So if we rearrange this expression a little bit, we end up with 1 over mu is equal to L squared over I. And now we're going to plug this expression into our expression for the Hamiltonian operator, and therefore we end up with a new expression for the Hamiltonian operator, minus h bar squared L squared over 2I multiplied by del squared. So here was del squared in terms of spherical coordinates. Remember, we didn't derive that. This was simply the result because that conversion was too tedious. And what we're first going to do with this del squared term, again, thinking about our specific case where we have a rigid rotor, what we're going to do is recognize here that this derivative in here, and certainly the derivative in terms of in the bracket here, since r is a constant and doesn't change, right, what we can effectively do is we're going to simply cancel for this particular system this first term. And so we're going to be left with an expression here for del squared. Now, with that expression for del squared, which I've repeated now in this next slide, but what you'll notice is if we go backwards in here, what we have in the very general expression is we've got these r squared terms in here, and with our r squared in our particular system, we're going to replace this simply with L squared. That's the label that we're using for the length of the bond effectively between the two balls on our rigid rotor. So remind ourselves, we're going to substitute L squared in for R squared. So what does that look like? This is how I get this next expression. So the only thing I've changed in here is I've changed it so that those R squareds are replaced by the L squareds. So now we have a del squared term in spherical coordinates that fits with the system that we're describing. So what else? Let's think about the Hamiltonian operator up here. Let's actually change the color a little bit. So we'll go to green in here. So there's our Hamiltonian operator. We've got an L squared in the numerator in here. So here's our L squared. And notice that we've got an L squared in the denominator of the del squared term. So when we substitute this del squared term into the Hamiltonian operator, what's going to happen is that we can cancel out those L squared terms. And so we finally end up with an expression that is minus h bar squared over 2i multiplied by this piece that's in our square brackets down here. We're not done yet, so there's a point to all this. So really we're just getting to a point where we understand what our Hamiltonian operator is, but we're going to learn something along the way. So earlier I said, let's remember what the kinetic energy operator is in terms of angular momentum. Okay, so angular momentum L squared or L hat squared over 2i. So really what we've just shown in the previous slide is, remember, we've got h hat is equal to minus h bar squared over 2I, and then in that square brackets we had 1 over sine theta di by di theta, sine theta di by di theta, plus 1 over sine squared theta di squared by di phi squared. Okay, so we'll put that in square brackets, and let's compare those. Let's compare these two expressions in here. Okay, so we know that h hat squared is the same as t hat squared in this particular case. Where we can go here is we can say, let's pull out L hat squared in here, and we find that L hat squared is given as this new expression down here. And the takeaway from all this, okay, here's our takeaway. It turns out that the square of the angular momentum, it naturally occurs all the time in quantum mechanics. We're going to find that going forward. There's an angular momentum square term that happens all the time. We found that came up even with Niels Bohr right back in week 1. There's just something special about angular momentum and quantization. So what else can we say about here in this expression? So note that we've got a theta term in here, and a phi term in here. So here's our phi term, and then here's our theta term in here. However, phi and theta are unitless. Okay, so what we recognize here is regarding angular momentum, it turns out that h bar is also very special. It ends up becoming a natural unit of angular momentum. So remember that, because we're going to start to quantize angular momentum for this rigid rotor. It's going to show up all over the place when we get towards the Schrodinger equation and our solution for the atom. But there's our takeaway here. What we still next have to do is put together our final Schrodinger equation and think about solving it, and we're going to do that. We're going to actually compartmentalize. We're going to break it down into a separation of variables approach. That will show up in the next lecture. So chopping this all up into bite-sized chunks, there's the takeaway today. H bar becomes a natural unit of angular momentum. We've now sort of introduced, this is not in table 4.1 on page 148, but what we have done in here is we found an operator for angular momentum squared, or L hat squared, and it's going to be very closely related to the Hamiltonian operator, right? And the only difference really here is this 2I down here. So energy and angular momentum squared is also seemingly connected. So let's see where that takes us in the next lecture. Thanks very much for your attention.